In a maintenance request to fix it. Okay, so again, the instantaneous rate is equal to the derivative. So in example 1, we first have to have a formula. You have a couple of problems like this on the homework where you want to just write out the formula, whatever it might be, if it's surface area or volume. If you're not sure of it, you can ask. And then the derivative. Now, the derivative can also be written dA dr. I want you to get used to both types of notation.
It's a capital A.
That's a capital A for area. So when we read this, so it says the rate of change of the area, so that's rate of change, so dA, with respect to the radius, so I put dr. So whatever it's with respect to, we put in the denominator. Okay, evaluate the rate of change of A when r equals 5 and r equals 10. Well, just plug it in.
Is that like
What's that?
compare the two values, like when r is 5 and r is 10?
Yeah, so let me explain. For the first one, okay, so you have this circle, right? It's growing, it's getting bigger, whatever. The area is changing at 10 pi square units, right when the radius is 5 units in length. When it gets to 10 inches, that's the radius, now the circle is getting bigger at a rate of 20 pi square units. So obviously it makes sense. As the radius gets bigger, the rate that the area is expanding is getting bigger and bigger.
Isn't the radius a secant for the circle though?
Oh no, we're just looking at it as a unit of measure. Just here you have a circle,
Yeah.
right? Here's the radius is 5. So that means the area here, like think of the area, is getting bigger at 10 pi square units. And then over here, now we have a bigger circle. This is 10. So this area, right, is getting bigger at 20 pi square units. It's just the unit. It's going to change depending on what type of problem we're looking at. So for part C, okay, if R is measured in inches and A is measured in square inches, what would be the unit for dA dr? Okay, it's like per. This is part C.
Part of B, like the same.
Yeah, I didn't give you units, but I kind of mentioned it. So if A is measured in square inches, so it would be inches squared per. What's dr? R is measured in just in inches. No, okay, hold on, let me.
The screencast.
It's fine.
The screencast. I'm just gonna go ahead and go with it.
Doing event system,
God.
all the Windows era.
Here, what you want to think about, what is area measured in? That's going to be square inches. A radius is measured in inches. So what if I said volume? Volume would be cube inch. Right. So you want to just look at, is it a linear measure? Like just the radius is measured in inches, feet, centimeters. But then area is measured in a square unit. Volume is measured in cubic units. And that's basically it. That's as much as you can get here. All right. Are we okay with that? Okay. So I think the question came up about one of the problems on the homework where it said S. S is almost always a position function. Sometimes it's X, but often you'll see the letter S. Okay, so suppose this object moves along a coordinate line. So the position function, so where it's located, is going to be a function of time. That's why it says here function of time. So like if you're talking about the motion, so this is where we get into like the overlap with physics. So maybe those of you that are in physics, we don't get that much in physics, but a little bit. Okay, but it makes sense. Like, okay, if you have a function, if you have something that's moving along an axis, what time it is. So like maybe at start time it's going to be at one location, and then 2 seconds later it's going to be somewhere else. So where it's located is a function of time. So it depends on the time that we're looking at. Okay, displacement. Displacement is basically how far it is from where it started from. So it's kind of like, let's say it's T1 to T2. So sometimes you'll see the delta, but often in calculus, we're just going to refer to like, this is where we are at the end minus where we are at the beginning. Okay? Make sense? So for example, if we use driving back and forth from home to school. So let's say you live 10 miles away.
And we get to school.
Okay, so if you live 10 miles away, so you have school and home. So from home to school, let's say it's 10 miles. So what's the displacement from home to school?
10 miles.
10 miles. Now what if you go back home?
20 miles.
No.
Zero.
Zero.
Because
Okay.
we just came back.
That's why I got a
Delta
D
X.
on my last
Delta
visit.
X.
That's what happened in physics.
It's.
Because he doesn't actually move from where he ended up. Like,
Okay.
his start position is the same as his end position, so he didn't get it.
The total distance traveled would be 20 miles because you went 10 miles one direction plus the 20 miles the opposite direction. But if you say your displacement, if I talk about, okay, at 7 in the morning we were at home, where are you at 7 in the evening at home if you've gone just from home to school and school back home? Exactly.
Calculating what you need to be.
Right, so that's what this is. This is your end position minus your start position. Average velocity. So average velocity is, this is very similar to what we had before. Average velocity is your average rate of change, which if you recall, that was your f of b minus f of a over b minus a. If you're referring to time, you can also write it like this. It's the same formula that we've used before. Okay, average rate of change, average velocity, because velocity is a rate of change, same thing.
So we can use this instead.
Yeah, I like using the t sub 1 to t sub 2.
Yeah.
Okay, instantaneous rate of change. Or sorry, instantaneous velocity, which is instantaneous rate of change, is the first derivative of the position function. Okay, this is where, so some of you were asking about why do we need these second derivatives or third derivatives. This is where they come in. So this is the first derivative of position.
What does that mean?
So you see how it has s prime? Later on we'll have s double prime.
S indicates position.
Okay, so S is the position. So think about, in terms of, we basically have three things that we're gonna, well, that's not true. But I guess if you start to think about, you have your position function, and then your velocity is your first derivative. Speed, so speed is just the absolute value of your velocity. So velocity can be measured in positive or negative. So for example, if you have, velocity has a direction to it, in other words, right? You could be moving forward or backward. If you're moving forward, you have a positive velocity. If you're moving backward, you have a negative velocity. However, the speed, you know, when you think about your speedometer in your car, it's always going to be positive. It doesn't like go backwards, you know, if you're going backwards from home to school or school to home. It's always going to say you're going 50 miles per hour, 35 miles per hour, whatever it is.
Radius velocity.
Right. Well, if you know what your velocity is, and let's say your velocity came out to be negative because you were moving in the negative direction, and I said, well, what's your speed? You'd say it's just positive. Just make it positive. Okay, acceleration. Acceleration is next. Acceleration is the second derivative of position.
Wait, so velocity is speed?
Speed is the absolute value of velocity.
Yeah. This is a velocity tells you if you got
Velocity has direction, speed does not. So when I talk about velocity, velocity has a number to it and a direction. So if it's positive, it's moving in a positive direction. If it's negative, it's moving in a negative direction. Whereas speed will just be a number. Okay? Now, second derivative. So that means my acceleration, it's kind of like, here's where you start. Then you have your first derivative velocity. And then you have acceleration, which is the first derivative velocity or the second derivative of the position.
Wait, could you just go up for 1 second?
What is position again? What,
Position is just where you are at a certain point in time.
so,
It makes more sense once you see like the examples that we're going to do.
Wait, do we have to know the English?
MA equals MG.
No, you don't need to have these memorized.
Okay, thank you. That's what I just.
These are just free fall constants. Yeah. You don't need to. So gravity, you know when you drop something, that gravity has a certain velocity. You don't need to have these memorized, but they're here if you need them. Okay? So we're going to take a look at this first, or this example here.
Why is physics
Okay, a dynamite blast.
I didn't say anything about it. It's not our favorite subject.
I go into that.
I promise, this is calculus.
I go into that class.
Then what the hell is physics?
It uses calculus. Okay. Oh, guys. Get over it and just learn.
You know what I
Okay.
wouldn't mind? I think astronomy. We try and do it around?
No.
Well, I want to go, guys, there's another example. So I'd rather go through this one together and then you guys can try, well, you have the homework also. All right. So let's take a look at the problem. This is not a difficult problem. If you have your calculator, you might want to have it out to help solve some of this. So this picture just shows the position. All right? So let's look at the problem. Dynamite blast propels a heavy rock straight up at a launch velocity of 160 feet per second. Okay. That's my velocity. Launch velocity. Okay, so that's not necessarily, that's kind of like what it's blasting it up into the air, right? So it's being shot up into the air. It's going to reach a height. So this is the position. Okay, that means, guys, so for example, if I said to you, where is the rock 1 second after the blast? We could plug in 1, and you could get the actual height of the rock. Or at 2 seconds, plug in 2, and you would get the height of the rock. Does that make sense? So the position in this case is referring to the height. The height of the rock. Later on, sometimes it's not necessarily height. It might be where it is on a certain axis. Okay. So how high does the rock go? Okay, so imagine at some point the rock has to stop going up and it has to fall back down. So if you look at the picture, you may see right here the rock at the top. It says V equals 0 because imagine when it's going up. So imagine here v is greater than 0, and then when it comes back down, velocity is less than 0. So it has a positive velocity going
It's
up,
always 0 at the top.
negative.
It's the direction it's headed.
Exactly. So what we want to do is, so when v of t equals 0, the rock reaches its maximum height.
Wait, how's 0? Oh, when it stops.
Right when it stops at the top, it's going to have a velocity of 0. Now, my position function was given here. So if we can figure out v of t, which is the first derivative of position, right? Okay, so go back up. 160t minus 16t squared. So now that we have all our shortcuts, derivative of 160t would be 160, right? Minus, now let's do that power rule. Move the 2 to the front so it becomes minus 32, and that would be t to the first. Are we okay with that derivative? Okay, so that's my velocity. Now I want to basically set that equal to 0 to figure out the time. Okay, so the time's going to tell me how much time it took to reach that maximum height. Does that make sense?
And so
5.
why is it 0 again?
It's
Because when
5,
at
right?
the top.
Yeah, because
It's
right,
always 0 at the top.
like if you throw something up in the air, right? It doesn't matter what it is. There's got to be a moment where it's actually stopped,
Stop.
and then it comes back down. So we're going to solve that.
It's 5.
Okay, so t equals 5.
So 5 seconds.
So I want to figure out s of 5. Why do I want to figure out s of 5?
That's how I
That's,
said it.
yeah, that's the
Yeah.
position.
Visualize.
So I have 160 times 5 minus 16 times 5 squared. And we get 400. Just,
Okay. I'm gonna do you this time.
Guys.
Try to speak with it. We have to put the units.
we are going to use units, yeah. Just feet. Okay. So looking at that picture, does that make sense?
It's
It takes 5 seconds to go from the ground to the maximum height. That maximum height ends up being 400 feet. And then it comes back and hits the ground. Okay. So now let's look at the next part. What is the velocity and speed of the rock when it's 256 feet above the ground on the way up and then on the way down? So if you look right here, it's labeled on the picture. So 256, it's going to reach that height going up and also coming back down. So it makes sense that one of them is going to end up being a positive velocity, one's going to be a negative velocity.
When it's,
It'd be the
when it's
same.
coming down, should we actually measure as 144?
No.
Because
The
that's starting to be
position, no, but the position itself is in relation to the ground, which is 0. So, okay. And we're going to run out of time, but here we have, when is,
Just leave that there.
we have to figure out when is the position equal to 256. So I have 160t minus 16t squared. I want to set that equal to 256. Just to save time, this is all divisible by 16, so it makes it a lot easier to work with. Okay. Are you okay if I move everything to one side at the same time or not?
Go for it, sure. Oh, we have to do one value.
This one factors, but you may have to do quadratic if it's not factorable. This one is. Just to save time, it does factor. So if you had divided everything by 16 and just moved everything so that t squared is positive, two numbers that multiply together to give us positive 16, add up to negative 10. Remember, you should get two answers, right?
But why are you putting it over 16?
Just to reduce it.
Oh yeah.
Just to make it easier. So t equals 2 and t equals 8. Right?
Yeah.
We have two answers. So on the way up, oops, v of 2 is 96. I know I'm going through this quickly. 96 feet per second. On the way down,
You just plug it.
yeah, you're plugging into velocity. And remember, we did the velocity function in the last part, so we could just plug it in there.
It's saying the
Where are you getting
velocity
96 from?
at 2 seconds.
Well, yeah,
You
wouldn't
plug
it
it
be the
into the
same?
equation.
Wait, what are you getting 96 from?
I'm gonna have to,
Wouldn't both be the same, just opposites of each other?
yeah, of course. Okay, where am I getting 96? Plug 2 into the velocity function that we found above. These should be the same, of
Wait,
course.
The 160c minus 16t squared, plug that in?
Yeah. No, plug it into this one. This one. Is that the one you
To
said?
the
160
derivative.
minus 32t.
Yeah, after
Oh,
you.
you
Yeah.
plug it into the
Plug it
derivative
into that one. Okay? You should, as long as it blasted off from the ground, it should end up being the same. Now, sometimes you blast it off of the top of a building and it hits the ground, then it's not going to be the same necessarily.
But that's
Can we go over it?
We could go over it again because we didn't finish this. So, again, we have tomorrow, or not, Thursday reserved for this. And I'll see you guys tomorrow.
You see this Thursday, right?
Okay. It's so much better if we had math every day. Well, then we could go slower and we could break it up into smaller pieces. But we got to cram in a lot of information, especially if we're finishing with seniors in March.
Yeah.
I know, but then it's we don't have any time to like spare. We have to get through everything.
What? Yeah.